Hello guys, welcome to Nerdsup. Today's topic is gradient descent. Gradient descent is one of the most important machine learning algorithm. What is gradient descent? Gradient descent is a first order iterative optimization algorithm for finding minimum of the function. To find a local minimum of a function using gradient descent, one takes steps proportional to negative of the gradient. What does these 2 points mean? So this is our graph where x-axis is the weight w and y-axis is j, which is a function of w. So initially we start off with some random weights. For this weight, the value of our cost function, that the error function, is this. The cost function is also called as error function, and we want to find this minimum, global cost minimum. We have to find the minimum of this function, so that we can find it by when we get this optimal weight over here. Obviously we won't find a function that can give us zero error, but this is the best we can do to find this point over here. So what we are going to do is, for every iteration we are going to take steps that is in the direction opposite to the gradient. We'll go down until unless we find this optimal weights where we find the global cost minimum. So I'm going to show you how we can apply gradient descent to a linear regression problem. But before that, let's talk about linear regression. What is linear regression? Suppose that you're given a bunch of points like these over here, and then you are asked to find the best fit line for these points. Obviously your line won't perfectly fit the data, but you'll draw a line like this where most of your data lies. So this is the best fit line for this data. And let's talk now about the equation of a line. Y is equals to bx plus a. Here this is the equation of the line. Here y is a function of x, and a and b are the weights we are that we will find using gradient descent, and they are also called as coefficient constants. A is the slope of the line and b is the y-intercept of the line. Let's talk more about the equation of the line. This is a line whose equation is y equal to 2x plus 1, where the value of b, which is the slope of the line, is equals to 2, and the y-intercept, which is a, is equals to 1. So how did you get the slope of the line equal to 2? How can you calculate the slope of a line? So the formula for the slope of a line is y2 minus y1 divided by x2 minus x1, which means that you take any 2 points that lies on that line, and then you plug in the values of those points over here. For example, over here in this formula, I plugged in the values of I've taken 2 data points as 0, 1 and 1, 3, and plugged in the values in this formula, and I got the slope of the line to be 2. And the value of y-intercept, which is a, is equals to 1 because this line intersects y-axis at this point, this red point over here, which is, so the y value of that point is 1. So let's so these are the steps to find a and b, the weights by gradient descent. These are the most important weights. Just remember this weight, these steps, guys. These are very important steps over here. So step 1, initialize a and b to random values. So remember, initially we start off with some random weights, and then we iterate over to find the optimal weights. So step 2, calculate the error function. We calculate the error by using the error function. And then step 3, we calculate the gradient, that is partial derivative of our error function with respect to each weights. Like over here we have 2 weights, a and b, so we calculate the error function with respect to each weight a and b to calculate the gradient. And then step 4, this is the most important step, we'll update the weights by using gradient descent. So the formula for updating the weight is new weight is equals to old weight minus learning weight into weight gradient, where weight gradient is the weight gradient is the gradient that we'll calculate in step 3, and learning rate is our hyperparameter that we will choose. Alright, and then step 5 says that we'll repeat step 2 to step 4 until we find convergence, which means that until for the next few we'll go on performing these steps 2 to step 4 until and unless, like, for the next few iterations we find that the weights are not changing much, the error is not changing much, which means that we have found convergence, and we'll stop our algorithm over there. The another stopping criteria we can consider is that if the error goes below a certain threshold, then we can stop our algorithm over there. So suppose that you have given you are given this table. These are the bunch of points, and you are asked to find the best fit line for this data. over here. So we'll use gradient descent for that. So let's start with step 1. We will initialize weights randomly. So over here is the slope. I have for the initial value for a is 0.45. It's just a random value that I've chosen, and b is the y-intercept. So the initial value for our b is 0.75, and our model, which is y equal to bx plus a, which is the equation of a line. So model for, let's do the calculation for data point 2, which is highlighted by this yellow points here, 0.22, 0.22. So the value of b in yp equal to bx plus a, the value of b is 0.75, the value of x for data point 2 is 0.22, and the value of a is 0.45. When we plug in the values in this formula, we get the predicted value of 0.62, which means that our model has predicted the value of y to be 0.62 and the value of x is 0.22, but actually the value of y is 0.22. So now we're going to add a new column to our table where we'll be computing yp equal to a plus bx for each and every data point. We did it for data point 2, like that we'll do it for every other data point 1, 3, and so on. Let's come to step 2, where we'll calculate the error function. I'm going to use error function as sum of squared errors. There are many other error functions like mean squared error, absolute error, but we'll be using for this example sum of squared error function. So sum of squared error function is equal to actual minus predicted the whole square divided by 2. So for data point 2, the actual value of y is 0.22 and predicted value is 0.62. We take the difference of those two numbers, we square it, and then divide by 2. We get the error for data point 2 as 0.077. So we're going to add a new column where we'll be computing the sum of squared error for each and every data point like we did it for data point 2. But we are not interested in the sum of squared error for a single data point. We want the sum of squared error across the whole training data. So we'll sum this column up to get the total sum of squared error across the whole training data to be 0.677. Now step 3, we will calculate the error gradient with respect to a, so which is the y-intercept. So when we take the partial derivative of the sum of squared error with respect to a, this is the formula that we get over here, minus of y minus yp. So y is actual and yp is the predicted y. For data point 2, the actual y is 0.22, so and the predicted y is 0.62. We'll plug in the values 0.22 minus 0.62, and then we will get the error gradient with respect to a for data point 2, 0.39. Again, we'll add a new column, and we want the error gradient with respect to a across the whole training data. So we are going to sum this column up to get the error gradient across the whole training data, which is 3.3. Step 3 continued. We'll calculate the error gradient with respect to b, which is our second weight, that is the slope of the line. And the formula, that is when you calculate the partial derivative of sum of squared error with respect to b, this is the formula that you get. Alright, so actual value, so we will be calculating it for data point 2. So actual value of y for data point 2 is 0.22, predicted value for y is 0.62. That's the prediction that our model made. And then input value, that is the x value for data point 2 is 0.22. We just plug in the values of these three in this formula, and then we get 0.09. That is only for data point 2. And then again we'll introduce another column which is the error gradient with respect to b, and we'll calculate it for every training data point like we did it for data point 2. We'll do it for data point 1, 3, and so on, and then we'll sum this column because we are interested in the error gradient with respect to b for across the whole training data. So we'll sum this column to get the error gradient with respect to b across the training data to be 1.545. And now step 4, guys. Step 4, this is the most important step. All right, updating the weights. New weight is equals to old weight minus learning weight into weight gradient. So new a, which is the new value of a, will be equal to old value of a minus learning weight into error gradient with respect to a across whole training data. So over here learning weight I have chosen is 0.01. So learning weight should not be too high or too low. If it's too high, which means that you may overshoot, I mean you may not find the optimal weight. You will miss that optimal weight. And learning weight, if the learning weight is too low, then your algorithm take a lot of time to convert. So I've chosen 0.01, which is I mean, you can experiment with learning rates. So 0.45 minus 0.01 into 3.3 gives you 0.42. So this will be the new value of a. Now when we will do step 2, step 3, step 4, we'll use the value of a as 0.42 and not 0.45. And similarly, the new v value will be old v minus learning rate into sum of squared error gradient with respect to v, which will be 0.73. And with these new weights, we will again perform step 2 to step 4, and when we perform this, we get this new table. We made this new table using these two values, which are the new values of a and b. And the important observation over here is that total sum of square errors across the whole training data over here is 0.553, and over here with these weight values it was 0.677, which means when we updated our weights, our error reduced, which means that we got one step closer to the solution. So, and now we'll do this steps 2 to step 4 again and again and again until and unless we find the convergence. All right. So, okay guys, this was the gradient descent algorithm, and then that's it for today, for this video. And in the next video we will code gradient descent from scratch, and we will use gradient descent to solve linear regression problem by coding it. All right. Okay, thank you guys. That's it for this video, and if you like our videos, then do subscribe to our channel Nerdsup, and please hit the like button. All right, bye, see you.